Hello, I'm Mark Foreman, and today we're going to delve into the farthest reaches of our visible universe and the very beginning of time. And from that, we can determine our future and the fate of everything. I'm going to create a hypothetical universe, which will have different amount of stuff than our real universe. In doing this, I will be able to then compare and contrast how this make-believe universe will behave differently just by twiddling three cosmic knobs that control fundamental properties. When we look into deep space, we're also looking back in time, all the way back to the afterglow of the Big Bang itself. This faint radiation, known as the cosmic microwave background, or CMB, is the oldest light we can see. It formed about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely through space, first light. This epoch is called recombination. I'll be discussing it shortly. First discovered in 1965 by Arnold Penzias and Robert Wilson, quite by accident, the CMB appeared as a nearly uniform microwave signal coming from every direction. Later, orbital telescope missions revealed that it wasn't perfectly smooth after all. There were tiny temperature variations, only a few parts in 100,000. These tiny ancient variations allowed gravity to form galaxies and galaxy clusters. The first big step in mapping those variations came from NASA's COBE satellite in 1989, which confirmed the CMB's blackbody spectrum and detected those faint anisotropies. Things weren't perfectly the same in all directions. Then came WMAP, launched in 2001, giving us a detailed map of temperature fluctuations across the sky. Finally, in 2009, the Planck mission from the European Space Agency gave us the sharpest view yet, measuring the CMB structure down to minute scales and refining our understanding of the universe's composition and geometry. The stuff of our universe can be broken down into three fundamental categories. These are the knobs I'm going to be twiddling. Baryonic matter, which is the normal matter that makes up protons, neutrons, electrons, which in turn make up atoms, which in turn make up stars, Earth, cats, dogs, me and you. Then there's dark matter, which is somewhat of a mystery. We know it's there from the gravitational effect it has on galaxies. A better term might be invisible matter, because it is completely undetectable as it does not interact with the electromagnetic spectrum. And lastly, there's dark energy. This is even stranger than dark matter, but we know it's there because it is steadily increasing the rate at which the universe is expanding. It's sometimes called the cosmological constant because Einstein added it to balance his equations in his theory of relativity. He later recanted it, stating it was his biggest blunder. Well, it turns out he was right to include it after all, just not the way he had intended. From those space telescope missions, scientists could precisely measure what are often called the three omegas, symbols that represent matter energy content of the cosmos. Omega B represents all normal matter, baryonic matter. Omega C accounts for the dark matter, the stuff that only affects the universe gravitationally, and omega delta, the cosmological constant, it represents dark energy, the mysterious force causing the expansion of the universe to accelerate. Using the online Planck CMB simulator, I was able to adjust these three omegas. On the left is our real universe, with 0.05, 0.275, and 0.675 respectively. You'll notice it has determined that this universe to be flat with a fundamental scale of about 0.8%. For my hypothetical universe, I selected my omegas to be 0.85, 0.175, and 0.05. Much more normal matter and less of the exotic dark matter and energy. Now, to compare these two universes qualitatively, the simulated CMB blotches are larger in scale, and the color variations indicate my cold is colder and my hot is hotter, indicating a higher anisotropy. Anisotropy. The power spectrum graph shows a huge first spike that's off the scale, with an L of 353, whereas the real universe is at 220. The next order spikes are much smaller in my universe due to the smaller proportions of dark matter and dark energy that I can figure. Quantitatively, the reason L is higher can be illustrated by the two equations formulated in the mid-1990s. L is proportional to pi over theta, and theta is proportional to R sub s over D sub a. Since a larger L means a smaller omega, and a smaller omega indicates a smaller R sub s, which is the physical size of the sound horizon, or a larger apparent distance D sub a to the CMB. In my universe, it's the R sub s that's smaller, because R sub s is affected by the sound speed, which in turn depends on the ratio of baryon to photon density. And I'll discuss this shortly, don't worry. Since my universe has a much larger baryon content, the sound speed is slower, since the photons have more mass to push around. Theta can then be determined by rearranging the formula and putting in the measured L value from observing the CMB. My universe is closed due to the fact that omega total, which is the sum of omega B, C, and delta, is greater than 1. Were it less than 1, it would be an open universe. Now I'm going to investigate some of the properties of my early hypothetical universe. In order to do so, I'll first introduce some universal constants. Recall that I only twiddled omega B, C, and delta. All other values and constants are the same as the real or benchmark universe. There's the Hubble constant, that's the expansion rate of our universe. Newton's gravitational constant, big G. Apéry's constant, which is the sum of the reciprocals of the cubes of all positive integers from 1 to infinity. That's used to ensure photon number counts are accurate when converting temperature to number density. There's the Boltzmann's constant, which is used to convert temperature to energy per particle. The reduced Planck's constant, h bar, which is the smallest chunk of energy, time, or momentum position that can exist. I'll be using the speed of light, the mass of a proton, and the binding energy of a hydrogen atom. We were given two values to work with: the cosmic microwave background temperature today of 2.7 Kelvin, and another omega R0, which is the present day radiation density. The last values I need are my hypothetical omegas of 0.85, 0.175, and 0.05. From these constants and values, we can calculate some fundamental properties of my early universe. I went for the baryon to photon ratio, the temperature of my universe at recombination, which I'll explain in a minute, and the temperatures at which radiation dominance gave way to matter, and matter dominance gave way to dark energy. To calculate the baryon to photon ratio, we must first know the critical density of the universe. That is, rho sub c equals 3 times the Hubble constant squared divided by 8 times pi times big G. Plugging in these values, I came up with about 9 times 10 to the minus 27 kilograms per cubic meter. Doing some additional math because I was curious, that comes out to less than 6 hydrogen atoms per cubic meter. Or, put another way, 130 quadrillion times less dense than the air we breathe. Now that I knew the critical density, which is rho sub c, I could then determine epsilon sub b, which is the baryon energy density, and epsilon sub gamma, the number density of photons. Finally, divide those two values, 4.68 per cubic meter divided by 4.13 times 10 to the 8th, I found my baryon to photon ratio of 1.13 times 10 to the negative 8. Flipping that over gave me 88 million photons per baryon. While that's a large number, it's 18 times smaller than the benchmark, our universe value of 1.6 billion photons per baryon, a factor of 18 times more. That shows my universe has much more matter in it due to my twiddle of omega B of 0.85. Let's move on to the temperature of the universe at recombination. First, what is recombination, right? Well, initially the universe was a super hot soup of protons, electrons, neutrinos, and photons. Dark energy was present as well, but it won't come into play until much later. The photons were bouncing off everything so fast, nothing could bind together before being smashed apart again. Finally, when the universe had expanded enough, it cooled down to where electrons and protons could find each other and form atoms, mostly hydrogen. In doing so, photons could then travel freely, the first light of the universe. So what was that cool temperature in my fake universe? For simplicity, we were told to assign the number density of ionizing energy photons to equal the baryon to photon ratio, rho, that I calculated earlier. So rewriting rho equals Euler's number raised to the power of the binding energy of hydrogen divided by the Boltzmann's constant times the temperature at recombination to solve for temperature, T sub rec, we see that 13.6 electron volts divided by 8.62 times 10 to the negative 5 electron volts per Kelvin times the inverse of rho basically computed out to a temperature of 8,500 Kelvin, or greater than 8,500 Kelvin. That's hot. The benchmark universe didn't recombine until it had cooled to less than 3,000 Kelvin, almost 3 times cooler. Since my fake universe has so much more matter, baryons, the photons have a harder time bullying it around, so my atoms could form at a higher temperature. Next, I calculated redshift, Z, and the scale factor of the universe at recombination. Here we go again. What do I mean by redshift and the scale factor? Well, I'll start with scale factor. That's easy. All it represents is how much smaller or larger the universe is compared to right now. Right now, the universe has a scale factor of 1. At some point in the past, it would have been at a scale factor of 0.5, meaning it was half the size it is now. A scale factor of 2 means twice the size. Now, redshift can be thought of as how far away in distance and time light is. Since our universe is expanding, the farther away something is, the redder it looks. Add in the Hubble constant, which shows it's not only expanding, it's expanding faster and faster. Far away things are very redshifted. The redshift of the farthest thing we can see, the CMB, tells us the size and age of our universe. The formula to determine the redshift at any time can be determined by dividing the temperature of the universe at that time by the temperature minus 1 of the universe today. Plugging in the temperature at recombination, 8,565 Kelvin, divided by the temperature today, 2.73 Kelvin, I determined a redshift of 3,160. Taking the reciprocal and adding 1, I uncovered a scale factor of 3.16 times 10 to the negative 4. That's 3/10,000ths the size of the universe today. Compared to the benchmark real universe, that's 3 times the redshift and 3 times smaller scale. This tells me that my universe reached recombination 3 times sooner when it was 3 times smaller than our universe. Now let's move farther forward in time since my fake Big Bang, to when matter energy equaled radiation energy. At this point, matter dominates and gravity starts to form familiar structures we see in the sky today. This is when the omega factors of mass and radiation are equal. As shown in the formula, 1 plus Z sub equals omega m over omega radiation. Omega M is the combination of baryon matter and dark matter, omega B and C. Rewriting to solve for Z sub equal and using my hypothetical universe values, 0.85 plus 0.175 divided by 9 times 10 to the negative 5 returns a value of 11,400. The scale factor is found with the reciprocal again, 8.78 times 10 to the negative 5. The benchmark Z sub equal is 3,400, and the scale was 2.9 times 10 to the negative 4. So my universe is 3 times younger and about 30% smaller when gravity finally got its chance to make a difference in the universe. And lastly, I wanted to determine if dark energy ever becomes important in my hypothetical universe, and if so, at what redshift and scale. Dark energy takes over when its energy density equals the energy density of matter, when rho m equals rho delta. Rho m has to take into account the scale of the universe, so it equals my omega m times the critical density, rho sub c, divided by the cubic scale factor. Rho delta equals omega delta times the critical density. It isn't affected by the scale factor. I told you dark energy was weird. Rearranging the formula to solve for the scale factor and plugging in the values, I determined that my hypothetical universe will be dark energy dominated at a scale of 2.74 and a Z of negative 0.635. That means my hypothetical universe is matter dominated to this day and will be until it has grown 275% larger. The negative Z also indicates this event is in the future. However, since omega delta is not zero, it will occur. For now, my universe will continue to expand slower and slower until it gets to almost 3 times larger, at which point the expansion will then start accelerating as dark energy becomes the big boy on the block. Now I'll move to the expansion history of my hypothetical universe. I'm going to focus on a moment during matter domination, after radiation, but before dark energy domination. I chose a redshift of 1000, which gives a scale factor of 9.99 times 10 to the negative 4. Using the density parameter form of the Friedmann equation, which includes 4 omegas, omega R0, omega m, omega k, and omega lambda, I calculated the expansion rate of my universe. We know omega R0, the present-day radiation density of 9 times 10 to the negative 5. We know omega m, the combination of baryon and dark matter omegas, 1.025. And we know omega lambda, dark energy, which in my universe is 0.05. Omega k is new. This is the curvature density parameter. If omega k is less than 1, the universe is open, more than 1, it's closed, and exactly 1, it's flat, like our universe. It's calculated by subtracting the sum of the omegas from 1. My universe is slightly closed because omega k is negative 0.0751. Plugging in all the omegas and my selected redshift, Z of 1000, I get 1.1 times 10 to the 9th for the right side of the equation. We're not done. The Friedmann equation requires the Hubble constant to be converted from 70 kilometers per second per megaparsec to the standard unit, 2.27 times 10 to the negative 18 per second. Now we can continue with the Friedmann equation and rearrange to solve for h. I calculated the expansion rate h when the redshift was 1000 to be 7.6 times 10 to the negative 14 per second. Putting that back into megaparsec form, that's over 2 million kilometers per second per megaparsec, roughly 33,000 times faster than our universe is expanding today. Next, I wanted to determine the curvature of my universe at Z1000. To do that, I first needed to calculate the critical density using the same formula I used earlier and determined that at Z1000, the critical density was 1.03 times 10 to the negative 17 kilograms per cubic meter. I then calculated the density of matter, radiation, and dark energy using today's critical density value calculated earlier, rho sub c, 0. That's 9.204 times 10 to the negative 27 kilograms per cubic meter. Finally, I got my omegas for this time frame, from which I determined omega k, the curvature, to be minus 4.5 times 10 to the negative 11. With an omega k effectively 0, my universe at Z1000 is flat. The last thing I wanted to know from examining my hypothetical universe at this time of matter domination was its acceleration rate. I've proved it is expanding, but is that expansion getting faster or slower? I hypothesized that it would be decelerating, because in a matter-dominated universe, gravity is king. I did the math to prove that hypothesis using the acceleration equation. The acceleration of my universe at Z1000 was negative 3.1 times 10 to the minus 27 per second per second. Another word for negative acceleration is deceleration. At Z1000, my universe was expanding, but that expansion was slowing by an inconceivable 3 million billion billionths of a second every second. On this plot, my universe would be near the bottom, just off the graph to the right, since my omega m is so large at 1.025, and my omega lambda is so small at 0.05. My universe would be just above flat, as my omega total is greater than 1. So, with this adventure coming to a close, what will happen to my make-believe universe that I created by twiddling the knobs of matter, and dark energy? It's expanding today and will continue doing so for a very long time, slowing in that expansion ever so microscopically as time goes on. Once it has expanded to when the density of matter will have dropped to where it equals the density of dark energy, then gravity will take a back seat and the expansion rate will reverse and begin to accelerate. The universe will ultimately meet its fate in a big chill. Those small red dwarf stars will have outlasted their bigger, hotter brothers and sister stars, but even they will run out of energy, and the universe will fade into darkness. Over trillions of years, even the black holes will evaporate. Ultimately, all that will be left are low-energy photons and neutrinos, as the universe cools toward absolute zero. Or will it? Thanks for sticking with me.